Hi everyone, welcome to GemChem. Now today's video is on spectroscopy, and in these videos we are going to deal with introduction, origin of spectroscopy, and the later videos will provide you information about rotational and vibrational IR and electronic spectroscopy. Now before starting, if you want to have a glance of other videos, I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first we are going to deal with what is spectroscopy. So in case of spectroscopy, it is the interaction between light and matter. And in this regards, we are going to deal with time dependent part of the Schrodinger equation, which is important for this case. And what is Schrodinger equation? If you want to know, I will give the link of that video in the description box as well as the I button. Now, these interactions involve different kinds of energy states, and the energy states for the matter is being defined by this time dependent wave function which is obtained from the Schrodinger equation. So what happens is that we consider light as a form of wave, and this interacts with the energy of the system, as a result of which we get a spectra. So what are the types of energy which is present in a molecule or a system? Let us see. First is that a molecule can vibrate and generate vibrational energy. Similarly, a molecule can rotate to produce rotational energy. Molecule transfer electron from one level to another, and this is also responsible for producing energy. Molecule has rotation of nucleus. Similarly, molecule has transfer of internal electrons to the outside vacant orbitals. So these are the reasons responsible to generate different kinds of energy. So if we consider here the energy gap which is created when a particle or when a subatomic particle goes higher up in energy, produces a resonance, and this resonance can be one of the reasons for production of spectrum. Now when we consider a theory which is perturbation theory, here it states that when we are going to apply light by matching the energy, then transition does not occur. Therefore, there is a transition probability which would help us to determine that whether the transition will occur or not. So in order to understand it better, property of matter is studied in terms of energy level. For example, from rotational energy of a molecule, it is easy to determine its rotational structure. Next, which is important to understand the spectroscopy, is Beer's law, which states that the difference in color of two substances generally occur due to the difference in their energies. And X-ray spectroscopy generally gives us the data electron present in the inner parts or inner orbitals are being ejected. So from here we can understand that for spectroscopy, interaction of light and matter is important, where matter can be considered as molecule and atom. So we need a detailed concept about light. When we talk about light, light has two components. One is electric component, another is magnetic component. So while using the light for spectroscopy, we generally use a polarized light which has only one component in it. So if we consider a wave of polarized light, we can see here that this is one complete cycle. This propagation of light ray is a harmonic motion, and the wave equation in terms of sine or cos can be expressed as y equals to a sine theta. Now what is y? Y is the amplitude at any instant of time, whereas this a is actually our maximum amplitude, and this a is also the radius of this circle. This y makes an angle theta with the radius, as a result of which we get this as y by a equals to sine theta, and from there we can get y equals to a sine theta. So from here, this is the direction of amplitude and this side is the direction of electric field. Now if we consider omega as the angular velocity in radian, then angle the wave will cover in time t will be equals to omega into t. So we substitute theta as omega t. For one complete cycle, if we consider, for one complete cycle it is time taken will be 2 pi by omega. So number of cycles which is covered in 1 second will be my frequency. As a result, it will become omega by 2 pi. So final equation comes to be as y equals to a sine 2 pi omega t. Now using this equation, if we further go, we have considered that in 1 second light is traveling c distance. If we see that c is our speed of light, we know that the unit of speed of light is meter per second. So from there only we can write that it is traveling c meters in 1 second. Then to travel x distance time, the required time is considered to be as t say, and it will be x by c in order to get the value. So finally, if we substitute this part here, then we get a sine 2 pi mu x by c, and already this is being known, c equals to nu lambda, lambda is the wavelength, we get our new equation for wave. Light is either expressed in wavelength unit or it is expressed in wave number unit, that is nu bar. And what is wave number? It is 1 by lambda. So when nu bar is increasing, energy will increase. When lambda is increasing, energy is going to decrease. Now for further study of spectroscopy, we need to have an idea of black body radiation, where we know that energy of oscillators is quantized. Change of energy is delta E equals to h nu. And for Bohr's model also, we need to have an idea of energy derivation. And this derivation is already being done in channel in atomic structure video. You can watch it. I will give the link in the description box as well as the I button present about this video. Next, we need to know de Broglie's wave particle duality, which also deals with that established dual property of matter, where lambda equals to h by mv, which is equals to h by p, and this equation is general when for particles wave property will be generated if mass is very small. And the last one is quantum mechanics, which we are going to deal with in a little explained manner. Now these are very important to understand the range where the different spectroscopy is being observed. For radio frequency, the wavelength is 10 meter to 1 centimeter and it is associated with your electron and neutron spin. For microwave, it is 1 centimeter to 100 micrometer, and this indicates association with rotation of molecule. For infrared, it is 100 micrometer to 1 micrometer and the vibration is along the bonds. Ultraviolet and visible 1 micrometer to 10 nanometer, and electron transition from one level to another in atoms and molecules. For X-ray, it is 10 nanometer, 100 picometer, and there is ejection of electrons from inner core. So in quantum mechanics, first thing, a general treatment which we are going to deal with is a box and a wave function. This wave function is generally considered as your xi, and this xi is your continuous well-behaved single valued complex function. From Heisenberg's principle, we have already seen that both position and momentum cannot be determined. So we are going to only observe the distribution of probability of position of a particle, and this can be given as xi star, and this both on being multiplied gives you real value. Schrodinger equation helps us to get or calculate the energy of the wave, and this is operated over using an operator to obtain an energy, and this is a general statement. Now what we need to do is, at first we developed, by using time and position x and t, a time dependent Schrodinger equation. Then at a steady state where t is constant, time independent Schrodinger equation was constructed. Now when we consider a particle to be very small, it becomes a wave in nature. So if we consider this box, which means that a subatomic particle, which is this dot, is confined in a nanometer or picometer box. 1 nanometer is the length of the one side of the box. Then what happens is that this box is considered as the molecular system, for which you can easily apply Newtonian mechanics, where particle has a finite size and box must have an appreciate length. To determine the energy, we are going to use our momentum and position, where the two coordinates are used to derive the energy and can easily predict those energies. But when we come to our subatomic particle, it is not easy to predict the energy using Newton's law. Reason is basically a particle, when we are considering so small, momentum and the position can't be predicted together, which is already being established by Heisenberg and de Broglie. So for subatomic particles, we are going to deal with Schrodinger's equation, which provides an equation of state corresponding to Newtonian mechanics. So if we consider this kind of operation, this is G, which is energy operator. When being operated, we get the wave function as well as a eigen value epsilon. So particle here behaves as a wave, and this energy operator is associated with both kinetic energy as well as potential energy. So in details, we are going to first see what is particle in box. Suppose we consider that a particle is being confined within a box with a length of a, and the starting point is x equal to 0 and the ending point is a. Now always remember that most simple quantum mechanical system is a particle in a box. Here we are not going to question about the potential energy, as in single particle they move freely and potential energy is minus e square by r. So fundamental criteria is momentum. Kinetic energy derived for this is in terms of momentum. So when we consider kinetic energy in general case, we have the expression as p square by 2m, right? And from quantum mechanical treatments and operation, we have obtained p to be equal to minus I h cut d by dx. Here then kinetic energy operator becomes like this: I square h cut square by 2m d square by dx square. This can be further written as, this h cut is actually our h by 2 pi. So we can write it as h cut equals to h by 2 pi, right? Now further it can be written as minus h square by 8 pi square m d square by dx square. So when operated on xi, we will get the energy. Now if we consider a condition where xi is discontinuous, what will happen? At that point energy will become infinite. So magnitude of xi at point x equal to 0 or at point where x is equals to a, then in that case your value for energy will be 0. Here the particle will not be able to exist. So here also xi is equals to 0, no particle, no wave function. Here also xi is equals to 0. So xi can simply be expressed by mathematical function sine curve, and a glance of expression of a wave is already being obtained in the previous slides. So my expression for xi will be equals to a sine n pi x by a. How many cycles we don't know. As a result, we are writing it as n pi. So if n is a fraction, suppose we consider n equal to half for x equal to a, then xi is not equal to 0. Thus we can say that we do not compare itself with a proposition, thus can be taken. So quantum mechanical restriction is crept in. So when n equal to 0, particle is in freeze condition, which is not possible. When n equals to +1, -1, plus 2, -2, then it is easy. When fraction is considered, then the proposition of xi equal to 0 is not important, because at that case range is deviating from its own sides. So in general, what is the equation for Schrodinger 1D case when we consider 1D box? In this case it is h square by 8 pi square m d square by dx square operated upon xi function plus your potential energy operator gives you eigenvalue and a xi, that is your wave function. So from here, if it is being operated by xi, we get this as h square by 8 pi square m n square pi square by a square xi equals to epsilon xi. So finally the energy comes to be as your this one, which is h square n square by 8 m a square. So for rotational and vibrational spectroscopy, there will be only change in the G operator. Nothing different will occur in other cases. And we are going to get different waves for that. Suppose when we consider this as xi 1, this as xi 2, this as xi 3, this as xi 4. That means this is n equal to 1, n equal to 2, n equal to 3 and n equal to 4. N can never be equal to 0. So in that case our wave becomes like this. So for xi 1 it is like this, for xi 2 it is like this, for xi 3 it is just like this, and for xi 4 it will be 4, right? So all acceptable xi values are present, and when we try to just express it with regards to your energy scale, then it is like this. You have here h square by 8m square, next you have 4h square by 8m square coming from this formula, next you have your 9h square by 8m square, and the last one is 16h square by 8m square. So different transitions are responsible to generate different spectroscopy. So energy state, and these are all stationary energy states. Okay. Now when the radiation is made to fall on the system, particle present in a one particular energy level will interact with the radiation and transmit to the higher energy level. When this occurs, we don't know what is required to derive the time dependent Schrodinger equation. So when particle comes from one state to another, there is a mixing of states, which is actually our wave function. So suppose we are considering xi L to xi m, in between there is a mixed function, thus they are not stationary transition, depends on time. Now if we talk about little probability, then if you see here xi equals to, we have already seen, a sine n pi x by a, right? Now probability we have already seen, it is xi into xi star. The xi star is complex conjugate of your xi. So probability can be written as integration infinity to minus infinity. So this will consider minus infinity to plus infinity, xi into xi star d tau. On integration we are going to get, this will be minus infinity means 0, and this is a square sine square n pi x by a, and probability is always equal to 1. So here in this case the normalization constant, that is a, comes to be as root over 2 by a. This is our normalization constant. So finally our wave function becomes like this: xi equals to root over 2 by a sine n pi x by a. When we try to draw the nature of probability, just take this like two columns. We have same way xi1 square, this is xi2 square, this is xi3 square, and this is xi4 square. So since now it is in the positive end, this will be like this. The two portions will be up. This will be 3 portions up, and this will be 4 portions up. Like this. All will be in the same size. Now the next one which is important for us to understand is orthogonality. Now in case of the values match electromagnetic radiation and energy differences, there will be transition. So what happens is that, suppose you consider here this as n equal to L, this is n equal to M, then once it goes up, it comes down due to the presence of a particular absorption as well as emission, and this is your xi m and xi l. So orthogonality provides us that integration of xi L star into xi m is equals to 1 when L becomes equal to m, and when xi L integration star xi m equals to 0, in that case L is not equals to m. And these all two things are applicable when we are considering our stationary state. So particle in a box, we consider the energy states to be stationary, but in spectroscopy we deal with absorption of light with time. As a result, always it is not necessary that the particles will stay in a stationary state. So what will be the character of wave function when we go from your xi m to xi l, that is your initial state xi m to your final state xi l? In that case, we are going to see that mixing of two wave functions occur. And finding out all the character of xi m, it will get converted to your xi l. And during these transitions, xi will depend upon time. So generally xi is represented as some am xi m plus al xi l. Am and al are time dependent functions, and gradually value of the coefficient is changing because this value is depending upon the mixing condition. If we consider this is L, so this will be L.